Hi, welcome to Hayward's Maths. If there's an example you're looking for, here's the list. Check out the one you need. Hope it helps.
So today we're looking at sample, proportions, and their distribution. So yesterday, what did we do? Recap. I introduced you to, or you rediscovered, relearnt, revised what yesterday? Sample, statistics, more information. When we survey everyone, it's called a census, and we're doing a survey of the whole population. And we're finding out what about the population? A parameter, very good. Alright, then if we do a survey of some of the population, what's it called? A sample survey, or just a survey, and it's a survey of a sample of the population, part of the population, and if we find something out about that, it's not the parameter, it's the statistic or the stat. Okay? So the two groups, so we're looking at, again, samples. So I introduced you to this thing called p-hat. It's pretty much the probability of that stat, pretty much, or the statistic, the outcome of that. So to figure out p-hat, it's the number of wanted outcome over the total number. Okay, so for example, I have a bag of chocolates. I have 20 chocolates, and I'm looking to pick a chocolate that doesn't have a nut in it. Okay, I know, the person I'm giving the chocolate to is allergic to nuts. So there's Snickers in here. I don't want to give them a Snickers. Okay? Now most of the time you don't know the parameter for the whole population. That's the whole point of a sample. But let's just imagine I do know the parameter. I know there's chocolates. Okay, so oh yay, he didn't die. What is the number of wanted outcome?
It's 7. There's one nut for normal.
One nut. How many total?
Well, you don't want the nut, you want the
I know. Wanted's probably the wrong word.
I want the nut.
The number of...
bad.
Yeah.
And this is where the outcome is not necessarily good or bad. Well, yeah, desired. But I guess you don't really decide, I don't know.
The total number of hours is 4.
Anyway, I think you've got the idea. There's one nut chocolate and there's 4 total. Okay, so the p-hat for the sample is?
1 over 4.
1 over 4. P, or what's the proportion for the total bag?
3 or 20.
Very good. So there's 3 nuts on 20. So you can see the sample has, is it a lower or higher proportion than the total?
Higher.
It's 0.25. This one is here. Quick maths. Okay? So you can see when we take a sample, is it necessarily the same as the total?
No.
No. So it's just an approximate. So that is called sample proportion. So then if we look at the sample, do you guys remember the symbol mu? What does mu mean? The mean, so in a sample, the mean is equal to p. In a sample, the standard deviation is equal to this equation. So p times 1 minus p over n, which is the number in the sample, square root all of that. So this is a very special and specific standard deviation formula. All right, and this is the algebraic version of that one I showed you before. So the desired outcome is capital X over the little n for a sample. So just get used to seeing, this is on your formula sheets, the standard deviation. So don't use that standard deviation formula for other stats, probability stuff that we've already done. Yeah, don't do that. It's only for a sample. Then we come to distribution. So this is an example in the textbook. Instead of chocolates, they had coloured discs or balls or something, and they had 20, and in the sample there was, in the 20 total population, there was 5 that were red and 15 that were blue. So what we could do is take a sample of 5 from that 20, right? And we could get from each individual sample, you could get 15,504 different samples from that 20 balls of 5 different balls. Within those 15,504 different samples, the proportion of the samples with 0 red balls is that frequency. Does that make any sense? So how did they calculate that? Has anyone figured out what these mean? Yep. So this is within the sample. We have 5 in the sample, 0 that are red, and this is outside the sample. 15 outside the sample, and 5 of those are red. So this is more or less the success times the failure, I guess, in other words. And it's going to produce that many samples. So out of the total number of samples, you're going to get this frequency that has 0 red balls in that sample of 5. Is that kind of making any sense? So if you just keep taking different samples, you're going to get 3,003 that have 0 red balls if you took 15,504 different samples. 1 red ball, 6,825. 2 red balls, 3 red balls, 4, 5 red balls. So you can see the probability of getting 5 red balls, or the relative frequency, is very, very low. There's a very low chance that you're going to get 100% red balls in your sample. I call it. What else? The only other thing you need to know is whether a sample is big or small. So any guesses what a big sample would be? So you're pretty much looking, is 10 times the sample number less than the total? And is n times p greater than or equal to 10? And this tells you if it's a large or not sample. You have a population of 1,000, that is 1,000 is equal to capital N. If you have a sample of 50, that's equal to little n. Okay, so if we sub these in, 50 times 10 is that less than 1,000? What if the probability of success is 0.1? 50 times 0.1, is that less than or equal to 10?
Less than 10.
It's not. So the sample is not large. So those are more or less your 2 checks. If one of them doesn't work, it's not large.